Our aim in this section is to find out the representations of the Poincare group by using the method of induced representations. Let me just remind you that we had already worked this much out, that if you take a state which is a simultaneous eigenstate of all the p mu's, the four components of the four momentum which commute with each other, and of course labeled by additional labels which you need to complete the identification of the state, and apply a Lorenz transformation of coordinates so that the corresponding operator u of lambda acts on psi p sigma, what you are going to get is a superposition of states with momentum lambda p, and this superposition can be written down in this form: C of sigma prime sigma with arguments lambda and p. So our job, of course, is to find out these numbers and especially find out the block structure so that we can identify individual single particle states. But as I already have said, finding out these numbers, that is, finding out the representation of the Poincare group, is not that simple simply because of the rather large size of the Poincare algebra and also the rather non-trivial commutation relations with the algebra elements obey. So we are going to try to look for a simpler way, which, as I have already stated, is the method of induced representations. Now, to understand what we are doing here, let us take a look at this point. Our problem really lies not only in the fact that the algebra is big, but also in the fact that the indices that we are using here are rather huge in number. Sigma, which is a collection of discrete indices, can be actually quite large in number. In fact, if you consider all possible particles in the world, then the sigma could very well be an infinite set. But it will be a discrete infinite set. On the other hand, P, the momentum, does not only belong to an infinite set, it belongs to a continuously infinite set, which is way more difficult to handle than the discrete indices sigma. It would be lovely if we could worry about just the sigmas for the time being and not worry too much about this continuous infinity of momentum values. Now, in order to do that, what we actually will try to do is try to work with the standard 4 momentum from which you can get your momentum p by applying a Lorenz transformation. Now, under a Lorenz transformation, a momentum, say, p goes over to lambda p, as we have already seen. The question that we are now addressing is, suppose I have a momentum, a fixed 4 momentum k. Can I go to p using a Lorenz transformation? The p that I actually have here. And the answer is, of course, not always. The reason is simple. Lorenz transformations leave certain things invariant. And if k and p have different values for those things, it would be impossible for you to change k into p by a Lorenz transformation. Now, what kind of invariants are we talking about? These are, of course, invariants which are functions of 4 momentum. And frankly, if you consider all Lorenz transformations, there are only 2 basic invariants. One of them is p square, that is p upper mu, p lower mu, which, let me remind you, in Weinberg's metric convention which we are using, it's minus p0 square plus p vector square. This is an invariant, it does not change under the Lorenz transformation. And also, another thing does not change under the kind of Lorenz transformations we are talking about. Remember, we are not talking about all Lorenz transformations really, we are talking about those Lorenz transformations which can be represented definitely by unitary operators, which are connected continuously to the identity. And that means we are talking about proper orthochronous Lorenz transformations. And under a proper orthochronous Lorenz transformation, the sign of P0, whether it is positive or negative, that does not change at all. But there's a catch here. You have to remember that this doesn't change provided you are talking of 4 momenta whose norm p square is actually negative. This might confuse some of you who may have thought that this happens when the norm p square is actually positive, but let me warn you that there you are using the high energy phases metric, so to speak, the one in which eta 0, 0 is positive and eta 1, 1, 2, 2, 3, 3 are negative. We are using a different metric. So for us, p square for a point particle is actually minus m square, where m is the mass of the particle, and not plus m square, which would have been the case if used the plus 1 minus 1 minus 1 minus 1 matrix. Of course, no matter which metric you use, ultimately you get the same result, that p0 square is actually equal to p vector square plus m square. But this is one thing about the convention that we are using that you have to keep in mind when you try to compare your results with those in other books. Because most books, at least most high energy books, would be using the plus minus 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 metric. We are using the minus plus 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 metric here. Okay, but having said that, these two quantities, p square and the sign of p0, do not change under a Lorenz transformation, assuming of course that we are talking of genuine particles where p squared is less than 0. That's for the second part, for the sign of p0 to stay the same under the Lorenz transformation. So if we want our force momentum p to come from some standard force momentum k by a Lorenz transformation, we have to ensure that k has the same value of k square as p square and same sign for k0 as p0. What that means is, for a given value of p square and a given sign of p0, we can choose a standard force momentum. All p which satisfy this particular condition, that p square is this fixed value and p0 has this fixed sign, positive for most useful situations, we are going to end up with one standard force momentum. What this implies is, for a given value of p square and a given sign of p0, we can choose a standard force momentum k, and all p which satisfy these conditions, that the norm is this value and sign of p0 is fixed, can be obtained from k by applying a Lorenz transformation. So not only do we have a standard momentum, okay, let's be more precise, standard force momentum k mu, such that you can get p mu by applying a Lorenz transformation on that. For every p mu, we choose a standard Lorenz transformation which does the job. Note that there are actually infinitely many Lorenz transformations which will change k mu into p mu. So this is something which you have to be careful about. When we say we are going to apply a Lorenz transformation to change k to p, we actually mean a precise standard Lorenz transformation which we are going to choose by convention. What particular k mu we are going to choose and what Lorenz transformation we are going to use as standard, that will actually depend on which particular case we are talking about, as we will soon see. So we will leave those details for later. For the time being, let me remind you, we are working with fixed p square and fixed sign of p0. We have chosen a k mu which has k square which is the same as this p square, and k0 which has the same sign as the sign of p0, and we are working with a standard choice of Lorenz transformation which will change the k to a p. Now the reason why we are introducing this is, the next question will be, what happens when we carry out this Lorenz transformation? In particular, what happens to the state psi k sigma when we carry out this particular Lorenz transformation? So U corresponding to L of p acts on psi k sigma, And this gives us something. Of course, this gives us a state whose momentum is P. And what we are going to do is we are going to define psi P sigma as this state. Well, not quite. For later convenience, we will see that it will be a nice idea to put in a normalization factor, which would very well depend on this momentum P. But apart from that, all you are saying is, given psi k with a particular set of discrete indices, psi for a momentum P with the same set of discrete indices, same sigma, can be obtained just by applying the Lorenz transformation or the corresponding unitary operator corresponding to the standard Lorenz LT or Lorenz transformation, which takes you from K to P. This actually defines how the psi P's for different sigmas are actually related to each other. Psi P sigma prime comes from psi K sigma prime by applying ULP. Psi P sigma double prime comes from psi K sigma double prime by applying ULP, and so on. So this is how you make a start. Why is this a good thing to start with? Ultimately, what we are going to see is we are going to refer every psi P sigma to this psi K sigma, which has a fixed 4 momentum K. As a result, the continuous infinity of P values is something that will not bother us so much. Of course, we still want to find out what an arbitrary Lorenz transformation, lambda, does to psi P sigma, and let's try to work that out now. So U lambda acting on psi P sigma, if you use this for psi P sigma, will simply be N of P, U lambda acting on ULP on psi K sigma. So these are two Lorenz transformations that you are carrying out in succession. First, the standard Lorenz transformation LP, then the Lorenz transformation whose action you are worried about. So this, of course, is U of lambda LP acting on psi K sigma. Just to check, what does lambda LP do to K? LP changes K to P, and lambda after that changes it to lambda P. So we end up with a final momentum or a state with a final momentum lambda P, as we should. After all, U lambda is acting on psi P sigma. The result, as we already know, is a superposition of psi lambda P sigma prime. Now, the next step will be something which may look a bit weird until you get to see the motivation behind it. What you will do is you will pull out U of L lambda P. But how can you pull it out? It's not even there. Well, you can pull it out by just putting in its inverse. So the standard Lorenz transformation, which takes you from K to lambda P, is being used here. Of course, this is just the identity. This changes nothing. So you still have whatever you had before. Lambda L of P psi K sigma. So basically, you have just put in this identity in here, changing nothing, of course. But the reason we do this is the following. You can now think of this as U of L lambda P acting on U of, now U inverse L lambda P is U of L inverse lambda P. So you can combine this Lorenz transformation with these two to end up with L lambda P's inverse lambda LP acting on psi K sigma. Now this seems to only complicate matters. So why we are doing this? Well, it will be clear if you just take a look at what this particular Lorenz transformation does to psi K sigma, or does to K first. Well, LP takes the momentum K to the momentum P, lambda takes it to lambda P, but L inverse lambda P, remember that is exactly the inverse of the Lorenz transformation which took K to lambda P. Now that the inverse is acting on lambda P, it will go back to K. So basically, this particular thing, which I am going to abbreviate with W, and of course W depends on both lambda and P, has this property that it's a Lorenz transformation. And what does this Lorenz transformation do? It takes the momentum K and carries it back to the momentum K. In other words, it leaves the momentum K unchanged, invariant. So W belongs to a subset of Lorenz transformations which actually keeps K fixed. So let me just take a leave from this calculation for a while and talk a bit about these Lorenz transformations which keep K fixed. So we are now going to consider a set of all Lorenz transformations W with the property that W acting on K, W mu nu K nu gives you K mu. Okay. So this is of course a subset of the Lorenz group, which formally is called SO31, or perhaps in Weinberg's notation should be called SO13. I'll have to check that. But it really means that it is like an orthogonal transformation, but the 3,1 says that you have 3 positive signs, 1 negative sign. Now, it is actually quite easy to show that this set forms a group in its own right. That is, elements of the Lorenz group which keeps a particular 4 momentum fixed, they obey properties like closure, which is rather trivial because if you take two such elements, W1 and W2, both of which keep K fixed, and apply them one after the other, the resulting transformation will of course keep K fixed. So closure is obvious. Associativity, this is a transformation, so all transformations are associative. We have already seen. Now if W is a Lorenz transformation, it has an inverse. In fact, this is a proper Lorenz transformation, so it has a determinant of +1, which guarantees that it has an inverse. And it's obvious that if Wk is equal to K, then K is equal to W inverse K. So W inverse also leaves K invariant. And by the way, I missed the identity, but it's obvious that the identity keeps K invariant, so the identity definitely belongs to this subset. So this is a subset which is a group in its own right, and that of course means it's a subgroup of the Lorenz group, and this particular kind of subgroup has a special name. It's called the Isometric Group, or more informally the little group of K mu. So this is where our nomenclature, the method of little group, comes from. In the process of finding out what U of lambda does to an arbitrary state psi p sigma, well, not quite arbitrary, this is a 4 momentum eigenstate, but these are the states that we are working with. We have figured out that you can break it up into 2 steps. Apart from the normalization, you have U of L lambda p acting after U of W lambda p acts on psi k sigma. And the beauty of W lambda p is W lambda p belongs to this little group of K, which means that it will not change the momentum K when it acts on psi k sigma. So let's go back and try to see what happens when U of W, any W belonging to this little group, acts on psi k sigma. Now this should be rather obvious that the result that you are going to get is going to be psi with K the same as this K, but possibly other values of the discrete indices. Remember, this W is not one of those standard Lorenz transformations. It's not one of the LPs necessarily. So it will not keep the index sigma the same. What you are going to get is a superposition here. D sigma prime sigma, sum over sigma prime, which of course depends. These numbers, d sigma prime sigma, definitely depend on the transformation W that we are talking about. But the important thing here is K doesn't change in the process. So it's only the sigma index which is of interest to us really. And this is a genuine matrix version of this operator U acting on W. We have already said before that linear algebra tells us why you have d sigma prime sigma and not d sigma sigma prime. But if you want to look at why, perhaps because you have forgotten your linear algebra or perhaps you did skip that class, let's take a look at what U W1 W2 will do to psi k sigma. What it should do, let me write that down, is that it should give me sum over sigma prime d sigma prime sigma according to this prescription. Of course, this d sigma prime sigma is a d set of d's corresponding to the Lorenz transformation W1 W2 psi k sigma prime. This is what I should get. But let's see what I do get when I think of U W1 W2 as a result of U W2 acting first, then U W1 acting on the result. Remember, we are talking about non-projective representations of the Lorenz group, which is a mouthful but which simply means that U of W1 W2 is U W1 into U W2 acting on psi k sigma. Now, this is U W1 acting on U W2 psi k sigma, and we know that U W2 psi k sigma should be D. Okay, just to ensure that we don't confuse with this sigma prime, let's call this D sigma double prime sigma. Of course, corresponding to the transformation W2, this is a different set of D compared to this one. Psi k sigma double prime. Of course, a sum over sigma double prime. Then UW1 will cross these numbers d sigma double prime sigma and go and act on psi. So what you are going to get is sum over sigma double prime d sigma double prime sigma W2, and then UW1's action on psi k sigma double prime will give you sum over sigma prime d sigma prime sigma double prime W1 psi k sigma prime. Now you can simply rewrite this by changing the order of the summation. Here the summation over sigma prime is being done first, then you are summing up over sigma double prime. But if you were to alter the order, what you are going to get is sum over sigma prime psi k sigma prime, and inside the bracket here what you will have is a sum over sigma double prime, and all we have to do is change the order of these two numbers to get something familiar. You are going to get d sigma prime sigma double prime W1. Sorry that I have to write this so small. I've left hardly any space for myself. D sigma double prime sigma W2. But this should be a very familiar object. This is exactly what you get when you multiply the two matrices dW1 and dW2 and try to find a sigma prime sigma prime element. So this is the same as d of W1, d of W2's sigma prime sigma element. Summing up over sigma double prime, so that goes away. Now let us compare the two results. We already know that UW1 W2 K sigma should be of this form. So d of W1 W2 sigma prime sigma element is sitting here. And what we have worked out using the fact that UW1 W2 is UW1 times UW2 is the following, that you actually have a sum over sigma prime psi k sigma prime into a bunch of coefficients, and these coefficients are nothing but the sigma prime sigma element of the matrix product dW1 dW2. So in the end what we have achieved is the following. These numbers d sigma prime sigma that we have written down are elements of matrices, and these matrices obey this result. D of W1 W2 is dW1 times dW2. In other words, these matrices furnish what in the jargon is called a representation, actually a matrix representation of the group which these W's belong to, which means of the little. Now, remember the little group is a set of those Lorenz transformations which keep K mu unchanged. We expect the little group to be a lot smaller and perhaps simpler than the Poincare group itself. We are looking at a much smaller subgroup here. And so, figuring out the representations of the little group would usually turn out to be a much easier task than figuring out all the representations of the Poincare group. So our job of identifying the way single particle states behave, identifying states which go with one single particle and so on, all of this hinges on being able to find out C sigma prime sigma, which you get when U lambda acted on psi P sigma. In this case, what we have is, as an intermediate step, we have introduced elements of the little group, and it is the little group whose representations that we need now. Once we have the little group representations, we should be able to find C sigma prime sigma, as I am going to demonstrate. So, the whole point is, the little group should be easier to handle than the Poincare group, and representations of the little group will tell you all about representations of the Poincare group. In other words, if you find D sigma prime sigma for W, you should be able to find out C sigma prime sigma for the lambda P. And that is what I am going to show now. Picking up from where we had left off, the result of a Lorenz transformation lambda acting on the state psi P sigma could be written down in terms of an action of a sequence of Lorenz transformations on our standard state, the state with standard 4 momentum K, psi K sigma. And it turned out that we have, apart from this normalization factor N of P, U of L lambda P acting after this particular Lorenz transformation, which happens to be a member of the little group. Now, using the representation of a little group that we had just studied, you can write this expression as sum over sigma prime d sigma prime sigma corresponding to this element W lambda P of the little group psi K sigma prime. Note that because of the fact that W does not change K, the momentum of this resulting state, or rather momentum of the states whose superposition gives us the result, all of them, is still K. And now you get U L lambda P to act on psi K sigma prime. And since L lambda P is the standard Lorenz transformation which carries K to the momentum lambda P, the result is pretty straightforward. You get N of P sum over sigma prime d sigma prime sigma. These are just numbers, so the U just carries through these numbers, goes and hits the psi K sigma prime. And what this gives us is psi lambda P sigma prime. Same sigma prime, remember, that's exactly what UL is supposed to do. And this is supposed to give you psi lambda P sigma prime up to this normalization factor, so you have to divide by N of lambda P. So the upshot of all this is, you have exactly figured out U lambda psi P sigma in terms of these representation matrix elements of the little group. And you can easily see that C sigma prime sigma lambda P, the numbers that we were trying to figure out, are nothing but NP by N lambda P, the ratio of the normalization factors which we have put in, times this matrix element D sigma prime sigma corresponding to W lambda P. Of course, W lambda P let me remind you, is nothing but L inverse lambda P, lambda LP. A Lorenz transformation which is composed of these three Lorenz transformations and something which happens to be a part of the little group of the four momentum chain. And let me emphasize once again, since the little group is usually smaller and simpler than the whole of the Poincare group, we should be able to figure out what these numbers are relatively easily, and that gives us a handle of what the original numbers C sigma prime sigma lambda P are. Also allows us to figure out what kind of block structure these numbers C sigma prime sigma may have, and hence identify what kind of possible behaviors different single particle states can have. All that remains at this stage is to figure out or decide by convention some choice for the normalization factors n of p, so that we can completely write down C sigma prime sigma in terms of D sigma prime sigma, which we can hopefully figure out from representation theory. We will next turn to this question of normalization of these wave functions, and that is what the next section will be about.